Namaskar. So in this lecture we will see about temperature dependence of resistivity, as you have discussed in our previous lecture about that how resistivity may be positive or negative depending upon the conductor, insulator or semiconductor, and also how different material may have a different temperature coefficient of resistivity. So here let's have a look at it and more better understanding about that. So let's begin. So for resistivity, let's say you have a resistivity for a given material at temperature T0 T, and at some reference value temperature T0 it is T, right? So let's say this is the temperature T and this is the T0. So for a limited temperature range, this relation can be given. It would look like something, or rho T is equal to rho 1 plus alpha T minus T0. So, but again, this is not for the whole range. There is a limited range, and we should know that in which range this equation can be satisfied, where it is a kind of a linear equation, where this term alpha is called temperature coefficient of resistivity. Temperature coefficient of resistivity. Right, and the unit of this, it can be temperature inverse. Okay, so for example, you remember when we saw in our previous lecture. So this you see here when we are talking about, so this was the temperature coefficient of resistivity alpha. This was the value which we are talking about in previous lecture, and that temperature at which it is given is 0 degrees Celsius. So that is important, and also we should know that where this equation holds well. Right. So there are other material, for example, if you talk about copper. So copper, if you talk about temperature less than 0 degrees Celsius, so in Kelvin you talk about 50, 100, let's say 150, in that range. If this is your temperature in Kelvin, I'm not talking about degrees Celsius, so it is still less than 0 degrees Celsius. And if this is the resistivity, so you'll find that no, it is not always linear below temperature. So again, the equation which we just discussed, rho 2 is equal to rho 0 1 plus alpha T minus T0, it is again valid for a limited range, and that is important. You can have for nichrome, you can have some exact relationship like this for T and K. There are material like, for example, semiconductor you talk about, right? So if you talk about rho and T, so with temperature their resistivity decreases. So here we can understand this, that why for semiconductors this decreases. If you see this table, you see this table, for metals it is positive, for semiconductor it is negative. So why it is negative? Why with the temperature it is decreasing? So to understand it better, first of all, as we already mentioned that when we are choosing the resistor materials, so it should be very less dependent on temperature. So that's why we went for these kind of material which have very low resistance, right? This temperature coefficient of resistivity, because with temperature the resistance doesn't change much, and that is what is needed as a device when you are going and depending upon that resistive value. Now talking back to that dependency of these negative positive, why for metals it is not positive and for semiconductor it is negative. So again, this can be understood with our equation which we had discussed, if you remember, when we are discussing the value of sigma which we had got, if you remember, n square tau upon m, where m is the mass of electron, number of electron per unit volume written as n, and this is charge of electron, and tau is the relaxation time, right? So now if you write it in terms of resistivities, you can write rho is equal to 1 upon sigma. It means you can write m upon n square tau, right? So it would mean that rho is inversely proportional to 1 upon n, and rho is inversely proportional to tau, right? So it means if tau is decreasing, your resistivity can increase, or if the number of electrons is increasing, then your resistivity can decrease. Okay, so now let's take the case of metal. So in case of metal, what happens? In case of metals, when you are increasing the temperature, so then what would happen? Then these electrons will vibrate, the atoms will vibrate more, and the collision of electrons will be more frequent. It would mean that the interval between two collisions, that is characterized by tau, that would reduce, means they will more frequently collide. So if in metals, if this is reducing, and of course in metals the number of electrons per unit volume is not going to change much with the temperature, because they are already free in free form. So n is almost unchangeable, but tau is decreasing. So in that case, you would see that if tau is decreasing, then your resistivity is going up, right? So if it is inversely proportional to tau, so it means that in case of metals, your resistivity will go up because tau is decreasing, because collision is going to be more frequent. But on the other hand, if you talk about semiconductor, so when you talk about semiconductors, right, so they are a material which are doped, and if you increase the temperature, the number of free electrons, the electrons which are available for conduction, is going to increase. So it means the number of electrons is going to increase. And on the other hand, if you talk about tau, even if they decrease, because the number of electrons are going to increase, so the tau will decrease, but the proportion by which n is going to increase much higher than what tau is going to be. So you see that in this case your n is going to increase significantly compared to tau, so your rho is going to decrease, right? So it is again dominated by number of electrons per unit volume in semiconductors, but in metals it is dominated by the relaxation time, which is going to decrease, and that's why it is resistivity is going to decrease. So this is about how the relationship between the temperature and how their resistivity is going to vary, and also at a certain limited range you can have a linear relationship, as we just discussed. And now you have a better understanding of that, why in semiconductors with the temperature your conductivity is going to decrease, or resistivity is going to decrease in the case of semiconductor, and in case of metals it is going to increase. Resistivity is going to increase, or conductivity is going to decrease. So this is all coming from your derived equation just before, where you have utilized the Ohm's law, and comes to that the relationship with the conductivity or resistivity, and how it is dependent upon the mass of electron, their relaxation time, and the number of electrons per unit volume. So that are realized. Now here we are proceeding in further direction. So this is all about temperature dependence. Now we'll discuss about electrical energy and power in our next lecture. So see you there. Thank you.